All right, welcome to video 10. So our first thing we'll talk about is the intermediate value theorem. So the intermediate value theorem, suppose we've got some function f that's continuous on a closed interval ab. Let n be any number between f of a and f of b where f of a does not equal f of b. Then there exists a number c in ab such that f of c equals n. So the reason this is starred is this is something you need to know exactly. Now the way you could write it, if you had to write it out, you could say if f is continuous on, and you can write the closed interval AB. Closed interval just means that it includes the endpoints, so you don't necessarily need to write closed interval. And n is between f of a and f of b, where f of a does not equal f of b. Then, okay, it's an if-then statement, there is a c in the open interval AB, meaning C can't be at the endpoints, such that f of C is equal to n. So again, that's starred because you need to make sure you know that definition exactly. You could be tested on that on quizzes and tests, final exam, things like that. So let's talk about what this means. So in other words, so f is continuous. So that means there's no jumps or anything like that, holes, on a closed interval AB. So that means our endpoints should be closed circles. And n is between f of a and f of b. Well, f of a and f of b are y values, so n is a y value. So it's saying we have some y value in between the y values of our endpoints, and it's saying the y values of our endpoints can't be the exact same thing. Then there's a c in the open interval AB. Well, c is a x value because it's in the interval AB, and they're saying the y value at c should equal n. So in everyday language, what this means is that if you have a continuous function on a closed interval, if you tell me any y value in between the y values of the endpoints, we are guaranteed that the function will hit it at some point. And let's see it with some pictures. So on the left is a case where maybe it only takes on the value once. So here's f of a, our y value of our endpoint, f of b, y value of our endpoint. Notice it's a continuous function between on that closed interval. Where we pick some y value n in between, we are guaranteed the function must hit n at some point. And now b there, that's just showing that it might happen multiple times. It's not necessarily just going to hit it once, but we're guaranteed that it hits it at least once. And that's just basically the same picture there. And the reason it has to be continuous is because if it's not continuous, you could have a jump that jumps over that y value, or maybe there'd be a hole at that y value, and then you're not guaranteed that it hits the y value. So that's why we must have continuity for that to be true. And we just talked about it, so it is important that it is continuous. All right, so we're going to now apply our intermediate value theorem. The most common way of applying the intermediate value theorem is using it to narrow down where roots are located. Because if we can show that one x value gives you a positive y and one gives you a negative y, so in this case we're going to use 1 and 2, then we know that it must hit every y value in between. Well, an important y value in between a negative number and a positive number would be 0, which is a root. So this is a key way of using the intermediate value theorem in mathematics. So let's do f of 1. Well, if we sub 1 in for x cubed and multiply it by 4, we get 4. If we sub 1 in for x squared and multiply it by negative 6, we get negative 6. And then we should get plus 3, and we'll get minus 2. So our positives are 7, our negatives are 8, so we should get -1. If we sub 2 in, 2 cubed times 4 should give us 32. 2 squared times -6 gives us -24. 2 times 3 is 6, and minus 2. So our positives should give us 38. Our negatives should give us -26. So altogether that gives us 12. So notice we got one y value that's negative, one y value that's positive. Notice this is a polynomial function. It's a cubic. Polynomials are continuous everywhere. So we are then guaranteed by the intermediate value theorem that we should take on every y value in between. So now we need to state that we're using the intermediate value theorem. So we're going to say by IVT. Okay, we can abbreviate it, the intermediate value theorem. There must be a root on the open interval 1, 2. And the reason we knew that was because there was the intermediate value theorem. Okay, and notice, again, it's on the open interval that we're guaranteed that there's a root, so it's not at those endpoints. Now, in reality, we could keep using the intermediate value theorem to narrow it down more. So this is just, I punched these in on the calculator earlier. So subbed in 1.2, got a negative number, 1.3 got a positive. So actually that narrows it down, and we know our root must lie between 1.2 and 1.3. And you could like keep doing that and narrowing it down further and further and further. And this is actually used on your calculator. When you go to find a root on the calculator, when you do menu analyze graph 0, it asks you to select a left bound and a right bound. Well, what you're doing is you're selecting one spot where a y value is positive and one spot where a y value is negative. So then as long as the function is continuous, the calculator knows that there has to be a 0 in between there, and it just searches in between those two spots that you picked. So this next statement is kind of obvious, but if f of x is continuous and there's no zeros, so if it never hits the x-axis at all, then we're guaranteed that f of x, so in other words our y values, are always positive or always negative. Okay? Because if you're not having any zeros, it means you're not crossing over to the other side. So for this one, we're going to see if we can determine where this function is positive and where it's negative. So what we need to do is we need to think about, well, what are the types of things that could cause a graph to change from being positive to negative or vice versa? Well, one of them is a root. And the other one is an asymptote. So we need to see where are our potential roots and asymptotes. And I guess hypothetically, you could have a hole that is right on the x-axis. Okay, and hypothetically that would also switch as well. So what we need to do is we need to factor this. So we'll have x minus 2 times x minus 2. And then the denominator will have x minus 3 and x minus 2. So holes are usually created whenever there is a factor that cancels out. But our factor that cancels out here, oops, my factoring's wrong there, sorry. That should be an x plus 1. So actually, there's no potential hole here because nothing cancels out. Our asymptotes are created from the things in the denominator that don't cancel out. So we're going to have asymptotes at x equals 3 and x equals -1. And then our zeros are when the y is equal to 0. Well, that means when our fraction is equal to 0. A fraction is equal to 0 when the numerator equals 0. Because if you have 0 over any number, that'll make it be 0. So in this case, our root will be x equals 2. So what we're going to do now is we're going to draw a number line, and we're going to put those things on a number line, because those are the spots where we know it could potentially switch from positive to negative or negative to positive. And then what we're going to do is we're just going to test the number in each and see if it gives us back a positive or negative. So let's start with this interval on the far left. Left of -1, we could try something like -10. And what we're going to do, we're going to sub it in for each of our factors here and see what it would give us. Well, if you sub -10 into x minus 2, you'll get a -12. So that's a negative times another negative. -10 put in the bottom would give us -13, so that's another negative. And then -10 plus 1 would give us another negative. So a negative times a negative is a positive, a negative times a negative is a positive, and a positive divided by a positive would give us a plus. So we don't really care what the number is, we just are trying to figure out if it's positive or negative. So something really easy in the next interval from -1 to 2 would be 0. So if we put in 0 in all the spots, we'd get a negative times a negative over a negative times a positive. Negative times a negative is a positive, positive times a negative is a negative, and when we divide a positive and a negative, we get a negative. Next section, maybe use 2.5. So we'll get a positive times a positive, and a negative times a positive. So that'll give us a positive over a negative, which is a negative. And our last section, if we put in something like +10 or so, we should get pluses everywhere. So we'll get a plus here. So we are positive for our y values from -infinity to -1. And then we're going to put a little u, that means the union. Okay, it means basically the first interval as well as the other interval. So then 3 to infinity is the other positive interval. And then negative, we have negative y values from -1 to 2. And then again from 2 to 3. Now we don't include the 2 because it's 0 there. That's neither positive nor negative. And the reason that it's negative and stays negative, if you think back to last year, you learned about when it's squared on top, because this is really x minus 2 squared, that's a bounce. So a bounce, it's coming from the negative side, and the graph is essentially at 2. It's coming from the negative side, and it's just bouncing there. Okay, and you should have saw that in pre-calc at the end of the year last year. All right, for most of the rest of the video, we're going to look at continuity. So for this one, they're going to tell us that we want to see when is f of x continuous, or if it is continuous at 3 and -2. Now, if they did not tell us that, say they just gave us this piecewise function on the right, the places you want to check for discontinuities are at the changeover numbers. So our interval switches over at -2 and switches over at 3. So that would tell us to check each of those. And then any place where your functions would be discontinuous. Where we have a linear, a parabola, and an absolute value, those would be all continuous everywhere, so we wouldn't have to worry. So we'd only have to check the changeover values. Okay, so this one tells us to check 3 and -2, but even if they didn't, we should be able to figure that out from our piecewise function. So when we do continuity, we want to do a 3-step check. So we'll do x equals 3 first. So our first step, we want to see what does f of 3 equal. So f of 3, that's going to be the middle function, because that's when x is less than or equal to 3. 3 plus 7 will give us 10. If that gave us, it does not exist, so like it gives you a 0 in a denominator or something, immediately then we are done and know it's discontinuous. But that worked out, so we'll go on. So we now need to do the limit as x approaches 3. Well, because 3 is a changeover number, we have to look at it from both sides to find the overall limit. So the limit as x approaches 3 from the left of f of x, and the limit as x approaches 3 from the right of f of x. Well, numbers to the left of 3 would be in our middle interval there, like 2.9, 2.99. So if we sub in 3 to that middle function, we get 10, because 3 plus 7 is 10. Coming from the right of 3, that would be like 3.1, 3.01. Well, that's that bottom interval. If we sub in 3 there, we'll get -3 plus 7, which is 4, and the absolute value of 7 would give us 4. Or sorry, absolute value of 4 would give us 4. Well, so now our overall limit as x approaches 3 of f of x. Notice from the left it was 10, from the right it was 4, so therefore our overall limit does not exist. If your limit does not exist, then we know it is discontinuous at that value. So we can write that it is discontinuous. When you're showing continuity, you got to do our 3-step process. Now, the third step would be if we got an actual number for the overall limit, we would then check in step 3 to see if our numbers from step 1 and step 2 are the same. All right, let's do the same thing now for x equals -2. So we'll do f of -2. The top interval is where we're equal to -2, so we'll sub that in and we'll get 5. Step 2, we've got to do the limit as x approaches -2 from the left of f of x, and the limit as x approaches -2 from the right of f of x. As we're going to the left of -2, that would be the top interval. Sub that in, we get 5. Right of -2, that would be the middle interval, and we would get 5 for that also. So our overall limit as x approaches -2 of f of x, from the left and right it was the same, so that was just 5. So now in step 3, we want to know, is f of -2, is it equal to the limit as x approaches -2 of f of x? Well, we found 5 for each of them, so that checked out. All 3 parts worked, so therefore at x equals -2, it is continuous. So when you're showing continuity, you should be doing the 3-step check, and if any of those parts fail, then we know it's discontinuous at that value. Okay, so here's another one. We want to see where f is discontinuous. Notice we've got a piecewise function, and it does not tell us where we want to check. So we definitely are going to check our changeover values, so at 0 and at 3. And in our intervals, the bottom 2 are always continuous, so those are fine. And in our square root function, we're subbing in only negative numbers, less than 0. And when you negate negatives, that gives you a positive under the radical, so we'll be good everywhere. We're defined everything in there. So we're going to do step 1, we'll do it for 0 first. So we'll do f of 0. The interval that includes that is the middle one. 3 minus 0 is 3. Step 2, we'll do limit as x approaches 0 from the left of f of x, and limit as x approaches 0 from the right of f of x. So left of 0 would be the top interval. When you sub in 0 to the top function, we get back 0. Right of 0 would be the middle interval. We sub in, we get 3. So our overall limit as x approaches 0 of f of x, from the left was 0, from the right was 3, so therefore this is a does not exist. So we would say we are discontinuous at x equals 0. So now we got to check for 3. So we'll do step 1, we'll do f of 3. We are equal to 3 in the bottom one, so when we sub in that, 3 minus 3 is 0, 0 squared is 0. Step 2, now we've got to do our limits. We'll do as we approach 3 from the left of f of x, and we'll do limit as x approaches 3 from the right for f of x. Left of 3 would be the middle interval. When we sub in 3, we get back 0. Right of 3 would be the bottom interval. When we sub in 3, we get back 0. So therefore, our limit as x approaches 3 overall from both sides, same number, so the overall limit is just 0. So step 3 now, we want to know, is f of 3, was it equal to the limit as x approaches 3 of f of x, the overall limit? And it was, 0 equaled 0, that checks out. So then we would say that it is continuous at x equals 3. So in reality, the way that this is worded, it says just determine where it's discontinuous. So technically this is just our answer, but we needed to do that work in the green in order to rule out that 3 was not also discontinuous. So you should show your 3-step check anytime you want to check discontinuities. All right, here's a graph. And this one wants to know at x equals 5. You don't have to copy down this graph. You can just follow along. Are we continuous from the right, continuous from the left, or neither? And remember, you're continuous from a single side if there's a closed circle on that side. So just some examples. So like at -5, there's a jump. Oops. At -5, there's a jump. And notice the closed circle is on the left. So we would say that -5 is continuous from the left. -3 would be continuous from the right or from the left as well, because there's a closed circle on the left. Let's see another place where there would be 8. It looks like there would be a continuous from the right, and then the other ones all have open circles. It's kind of hard to see the open circles, but they're there. Now at 5, there's an asymptote there. There's no closed circles on either side. So we would say for this one that it is neither. Okay, it is neither continuous from the left nor continuous from the right. And what that's just saying is, can you actually get to that x value all the way? Well, if so, can you get to it all the way from the left side or from the right side? Or if not possible, it would be neither. All right, next one, we want to find this limit. Well, to evaluate a limit, okay, if you've got an absolute value, we're going to want to write it as a piecewise function. So we need to think about absolute values and what they do. When you have a positive number in an absolute value, when you take its absolute value, it does not change it. But when you have a negative number in an absolute value, it switches the sign. So what we need to do for this absolute value that's on the bottom, we need to think about when is it positive and when is it negative. It is going to be positive whenever x is less than 2. It is going to be negative when x is greater than 2. And when I'm saying positive and negative, I mean the inside of the function there. And then you can pick where you want to put the equal to. So let's maybe just throw the equal to on this one. Because the 0, it doesn't matter for it. So what this means is, for that top section, when x is less than or equal to negative, or x is less than or equal to 2, the absolute value will not change what's inside the function. So in other words, the function will still just be 2 minus x for any x values that are less than or equal to 2. But for the second section, when x is greater than 2, because the number inside will be negative, we will end up negating what's inside. Like if we got -7 inside, we would negate it and say the absolute value is +7. So to be able to write this without the absolute value, when x is less or greater than 2, our function would be -2 plus x. And where that's coming from is it's negating both parts. So what we're going to do is we're really going to write this as a piecewise function. This function we're working with, we'll call it f of x, is really equal to 2 minus x over 2 minus x when x is less than or equal to 2. And it's going to be 2 minus x over minus 2 plus x when x is greater than 2. So that's really what we have for our absolute value. And when you have an absolute value in a limit, you're going to usually have to do this in order to evaluate it. Because really an absolute value is just 2 separate linear functions. That's essentially what we're doing. So to evaluate this, we got to do the left side and right side limits. Let's do limit as x approaches 2 from the left. Well, left of 2 would be the top function. So we're really just doing 2 minus x over 2 minus x. Well, that's really just the limit as x approaches 2 from the left. That's the exact same thing, so it's just 1. So we get for the left-hand limit that it's just 1. Now when we do our limit from the right, limit as x approaches 2 from the right, we'll use the bottom. We'll have 2 minus x over minus 2 plus x. Well, on the bottom, we can pull out a -1. And that would give us -1 times 2 minus x. Well, now notice the 2 minus x's match up. So this is just going to be the limit as x approaches 2 from the right of 1 over negative 1. So that's just going to be a constant for our limit of negative 1. So what this is saying is, on the left of 2, we'll be approaching 1, but the right of 2 will be approaching negative 1. So our overall limit then of f of x does not exist, because the left side and the right side are not the same. Now, you want to be comfortable being able to write an absolute value as a piecewise function, okay, being able to write it separately. And all you're doing is writing an interval where the inside is positive. That's just going to be the inside of your absolute value. And write an interval where the inside is negative. That's going to be the negation of your inside. That's it for this video. We'll see you next class period.